Chapter 5, Section 3, Matrix Representation of Linear Transformations. In this section, you will learn what matrix representation of a linear transformation is, why matrix representation is important and useful, and major examples of matrix representation. The matrix representation of linear transformations refers to the method of expressing linear transformations using matrices. By using matrices, we can clearly describe how the entire vector space is transformed through mathematical operations. It makes calculations more straightforward. Moreover, matrix vector multiplication provides an efficient way to apply transformations and combine multiple transformations. Matrix representation of linear transformation is the process of expressing a linear transformation as a matrix and using that matrix to transform vectors. A matrix itself is not a geometric object, but rather a tool or operation that represents a linear transformation. By using matrices, we can perform various geometric transformations, such as rotation, scaling, reflection, and shear within a vector space. In mathematical notation, the multiplication of a matrix and a vector is usually expressed with the matrix on the left side of the vector. This order indicates that the matrix represents the operation of the transformation, which acts on the vector. Let's see an example of matrix representation of a linear transformation. Let's consider linear transformation T in a two-dimensional space, where vector v is transformed in this way. This transformation can be represented in matrix form in this way. This matrix transformed the vector v into a new vector. In this way, the matrix provides a clear way to map the original vector v to a new position in the transformed space. There are several advantages of matrix representation. The first is efficient calculations. Matrix vector multiplication enables fast and efficient computation of transformations. The second is easy combination. Multiple transformations can be combined into one transformation by multiplying their matrices. The third is clear mathematical representation. Matrices can express the properties of linear transformations, such as additivity and homogeneity. Now, let's see how we can represent some representative types of linear transformation using matrix. The first is rotation. Rotation is a transformation that rotates the entire space around the origin by a specified angle. In a two-dimensional space, the rotation matrix for an angle theta can be expressed in this way. For example, we can express a linear transformation that rotates the vector v by 90 degrees in this way. Next, scaling. Scaling is a transformation that uniformly increases or decreases the length of all vectors by a fixed ratio. A scaling matrix can be expressed in this way. Here, k is the scaling factor. For example, a transformation that doubles the vector v can be expressed in this way. The vector's direction remains unchanged, but its length is doubled. Next, shear. Shear is a transformation that stretches the entire space in one direction. Shear in the x direction can be expressed by this matrix. Here, K is the shear strength. For example, applying shear with K equals 2 to the vector V can be expressed in this way. The vector has been stretched in the x direction. As the final example, let's see reflection. Reflection is a transformation that flips the entire space around a specific axis. A reflection matrix around the x-axis can be expressed in this way. For example, reflecting the vector v across the x-axis can be expressed in this way. The direction along the y-axis has been flipped. The matrix representation of linear transformations expresses the transformation as a matrix acting on vectors as a tool that performs operations such as rotation, scaling, reflection, and shear. These transformations follow the properties of linearity, additivity, and homogeneity. They maintain the relationship between vectors while keeping the origin fixed. These geometric transformations are important in practical data analysis and machine learning applications. We can apply linear transformations to manipulate data to reveal patterns and relationships. Thank you for watching. Please thumbs up and subscribe to my channel.